Hello friend, welcome to this new video. In this video we prove one beautiful theorem of integrability of product of two functions. If we have two integrable functions, then here we will prove that the product of these two integrable function is also integrable. The statement of the theorem is that if we have f1 and f2 are two bounded and integrable functions on closed interval a comma b, then the product f1 into f2 is also bounded and integrable on closed interval a comma b. Now let us prove this. So first it is given that f1 and f1 f2 are bounded and integrable on closed interval a comma b. Therefore there exists k such that k is a number such that all the values of the function f1 of x is less than equal to k and f2 of x is less than equal to k. But this implies that mod of f1 into f2 of x equal to, this is mod of f1 of x into f2 of x equal to mod of f1 of x into mod of f2 of x. This is less than equal to k square. And if we take f equal to f1 into f2, therefore f is bounded. This gives us f is bounded on closed interval a comma b. Now let p star, p is a partition. Let us take p is a partition having this point x1 x2 dash dash xn, which is nothing but b of closed interval a comma b. And suppose that capital Mi comma small mi semicolon capital Mi dash comma small mi dash capital Mi double dash comma small mi double dash be the supremum and infimum of the function f, f1, f2 in delta xi. This is a subinterval. So in this subinterval, these are the supremum and infimum of f, supremum and infimum of f1, supremum and infimum of f2. Now consider any 2 point. Consider x1 comma x2 belongs to delta xi. Then we can see that f of x1 minus f of x2, this is nothing but mod of f1 f2 of x1 minus f1 f2 of x2. Okay, what is this? This is f1 of x1 f2 of x1 minus f1 of x2 f2 of x2 modulus value, okay, equal to mod of f1 of x1 f2 of x1 minus f1 of x2 f2 of x2. Let us add and subtract this point plus f1 of x2 f2 of x2 minus f1 of x2 and f2 of x2. we consider this is as f2 x1. Okay, if we take it as a f2 x1, f2 x1, we need this f2 x1, right? Okay, now we are adding and subtracting the point f1 x2, f2 x1 here, mod. Then from the first two you can see that we can take f2 x1 as a common term, and from the second two we can take f1 x2 as a common term. Then we have mod of, therefore you can see that mod of f of x1 minus f of x2 is less than equal to mod of f2 of x1 into mod of f1 x1 minus f1 x2, and in the second bracket mod of f1 x2 into mod of f2 x1 minus f2 x2. But f2 x1, this is a less than equal to k, this is less than equal to k, and the modulus value, this modulus value is less than equal to, let us take the supremum of this. So this is less than equal to mi dash minus small mi dash, and this is capital Mi minus small mi. Supremum values of this, supremum of this, by applying the theorem of oscillation of the previous video, the mod of f of x1 minus f of x2, this supremum of this set is mi minus capital M minus small m. So k into capital Mi double dash minus small mi double dash. Okay, we have this equation. Now we choose this partition P such that the norm of this is less than delta. Now taking summation over this, all this capital Mi into delta xi, I is equal to 1 to n, minus summation of small mi into delta xi, I is equal to 1 to n. This is less than equal to k into capital Mi dash into delta xi, I is equal to 1 to n, minus summation of small mi dash into delta xi, I is equal to 1 to n, plus second term k into capital Mi double dash into delta xi, I is equal to 1 to n, minus summation of small mi double dash into delta xi, I is equal to 1 to n. But what is the capital summation of this? Summation of this is nothing but an upper sum and lower sum. So this gives us upper sum minus lower sum. This means that the UPF1 into F2, F is a F1 into F2 minus LPF1 into F2 is less than equal to K into UPF1 minus LPF1 plus K into UPF2 minus LPF2. Functions are integrable. Again apply that f1 and f2 are integrable, therefore for epsilon greater than 0 there exists a partition P with norm mu of P is less than delta, his P is less than delta, such that this UPF1 minus LPF1 is less than epsilon. Here we take epsilon divided by 2 into k. These are less than any value, therefore we take this value, and UPF2 minus LPF2 is less than epsilon divided by 2k, but then this UPF1 into F2 minus LPF1 into F2 is less than k into epsilon divided by 2k plus k into epsilon divided by 2k k get cancel and we get epsilon divided by 2 plus epsilon divided by 2 equal to epsilon. Upper sum minus lower sum is less than epsilon and therefore the function is an integrable function. So here we have f1 into f2 is integrable over a closed interval a comma b. So we have shown that as the f1 and f2 two functions are integrable, their product is also integrable over the same interval a comma b.